This activity is called Interior Insights. In this activity, you will use plasticine to create a three-dimensional model of the structure of the Earth. Use different colours and thicknesses to represent the core, mantle and crust, and then cut your model in half to reveal the layers. These are the compositional or chemical layers of the Earth that are based on the material that makes up the rocks at each layer. The structure of the Earth can also be described as having mechanical layers. That is, whether the material is rigid like solid rock or fluid like molten rock. You may like to also build a three-dimensional model of the mechanical layers of Earth. In primary science, using three-dimensional models to represent scientific phenomena can assist students in developing their conceptual understanding. However, it's a good idea to have students evaluate the strengths and limitations of their model. This activity is called Changes Over Time and investigates the changes to Earth's surface over the last 200 million years. Recall from Activity 1 that the lithosphere is the outer layer of the Earth and includes the crust and the top of the mantle. The lithosphere is broken into tectonic plates, which are huge slabs of material that are constantly moving, in part due to the convection of the hot material beneath them in the mantle. The movement of these tectonic plates throughout geological time is called continental drift. This is because Earth's continents are part of tectonic plates and appear to drift across the Earth's surface as the tectonic plates move. You can see that Earth's surface looked very different 200 million years ago. Then they separated further into two supercontinents called Laurasia and Gondwana land. Watch as they separate over time due to tectonic plate movement. Although it might be difficult for you to do this activity at home if you're an online learner, there are continental drift jigsaw puzzles that you could print and arrange in order to find out what the Earth's surface might have looked like 200 million years ago. Here's one that I've printed from an educational website. This activity is called Explaining Earthquakes. In this activity, you will explore tectonic plate boundaries and the types of landforms that occur at these places. Remember from Activity 2 that the lithosphere is broken into huge slabs of material called tectonic plates that are constantly moving. While some tectonic plates may have continental lithosphere at their edges, like here for example, others may have oceanic lithosphere at their edges, like here for example. The places where two tectonic plates meet are called tectonic plate boundaries, and they are geologically active areas where mountains and volcanoes may occur, or where earthquakes may occur. In these areas, tectonic plates may move towards each other, and these are called convergent tectonic plate boundaries. At a convergent plate boundary, which has continental lithosphere and continental lithosphere at its edges, both tectonic plates push upwards, folding to form a mountain range. This is how the Himalayas mountain range was formed. At a convergent tectonic plate boundary that has continental and oceanic lithosphere at its edge, the oceanic lithosphere, which is more dense, subducts beneath the continental lithosphere, pushing it upwards, also forming a mountain range. As the oceanic lithosphere subducts, it can start to melt, also causing volcanoes in these areas. This is how the Andes mountain range in South America was formed. This map illustrates nicely how the Himalayas was formed at a continental-continental convergent plate boundary. However, the Andes was formed at a continental-oceanic convergent plate boundary. Tectonic plates may also move away from each other, and this is called a divergent plate boundary. If this occurs at a continental-continental divergent plate boundary, as the tectonic plates move apart, the lithosphere starts to thin. The lithosphere can break in some places as it's thinning, and this causes the magma from below to rise to the surface and form a volcano. This landform is called a continental rift valley. For example, the East African Rift started forming and the lithosphere started thinning out 25 million years ago. This can also occur at oceanic divergent plate boundaries under the ocean, where the tectonic plates spread apart and new ocean floor rises to the surface and cools down. There may also be areas at tectonic plate boundaries where tectonic plates are moving alongside one another. This is called a transform plate boundary. In these areas, the tectonic plates move alongside one another and they catch. The pressure builds and builds until it is released in a seismic slip that causes an earthquake. Try building your own models of tectonic plate boundaries using plasticine and show what landforms would have occurred over the millions and millions of years. In this activity, Volcanoes and Rocks, you will observe three types of rocks: sedimentary, igneous, and metamorphic. You'll pay particular attention to the igneous rocks and group them as extrusive or intrusive igneous rocks. Here you can see some igneous rocks, including granite, basalt, and pumice. Igneous rocks are formed from magma below Earth's surface. This is easy to remember because the word igneous means from fire. You might notice that these igneous rocks look very different to each other. This is because there are two types of igneous rocks: those that have cooled down very slowly deep beneath the Earth's surface, and those that have cooled down very rapidly at the Earth's surface. Igneous rocks that have cooled down very slowly have got large crystallized minerals that are visible with the naked eye. These rocks are called intrusive or plutonic igneous rocks. Some examples include granite, rhyolite, and gabbro. Igneous rocks that have cooled down very rapidly do not have crystallized minerals and are called extrusive or volcanic igneous rocks. Some examples include basalt and pumice. The other rock types are sedimentary and metamorphic. Sedimentary rocks are identifiable by their layers of sediment, which have been deposited, compacted, and cemented over geological time. Metamorphic rocks are identifiable by their stripes. Metamorphic rocks are igneous or sedimentary rocks that have been deformed deep below the Earth's surface by immense pressure or heat. Some examples include schist or granulite. You might like to have a look at some rocks in your backyard or at the local park to see whether they have dots, layers, or stripes, and therefore whether they're igneous, sedimentary, or metamorphic rocks. In this activity, So You Want to Be a Seismologist, you will simulate an earthquake and create and analyze a seismogram. Seismologists use instruments called seismographs to measure the seismic waves or energy waves released at an earthquake. They produce a seismogram or a graph that gives lots of information. It tells us where the earthquake occurred, that is, where was its focus and epicenter, and how much energy was released by the earthquake, that is, its magnitude. You will need some helpers for this activity. One person will hold a pen just above a piece of paper on a desk. A second person will shake the desk from side to side to simulate the earthquake. And a third person will pull the piece of paper along the desk. The energy released by an earthquake is carried through the crustal rock as different types of waves. When the waves arise at Earth's surface, they cause the ground to vibrate. Primary waves, or P waves, travel faster than secondary waves, or S waves. Although your seismogram might not look perfect, see if you can identify some P waves and S waves. The P waves arrive first, and the S waves arrive later on. We use information on these seismograms to help us work out where an earthquake has occurred and what an earthquake's magnitude is on the Richter scale. Try this activity at home and see if you can be a seismologist on your own.